Good morning, Pass. Welcome to this year's edition of Ridiculous Optimizer Tricks to Impress Your Dev and Freak Out Your DBA. I'll be your guide today. Please silence your cell phones. If your cell phone goes off, you'll have to wear Arginus's unicorn hoodie. You don't want to do that. And the kilt, too. And he'll take it off for you. And so it's really bad. Don't do it. So, 2 years ago, 2012, I delivered the first edition of this talk, actually in this room at this time, so this is kind of a bit of flashback. And we'll do a little bit of review from that talk, and then we'll jump into the new material. This talk is kind of an extension of what I talked about last time, so hopefully most of you have seen some version of that talk. So that was the art and science of manhandling parallelism. I took out all the art and science this time, and we'll just manhandle parallelism. So the main point of the talk was that what we want to do is figure out how to process our data ideally when we're going parallel. And ideal parallel processing means that if we start up, for example, 8 threads, all 8 threads will start, all 8 threads will do as much as possible an equivalent amount of work, and then all 8 threads will finish at the same time. We want to avoid skew. We want to avoid a situation where, for example, 7 threads or 8 threads start, 7 threads finish after 1 second, and then the 8th thread runs for 10 minutes. That's a waste of time. That's a waste of resources. We want equal work distribution. That's what good parallel processing is all about. So we talked about that a little bit. Also talked about Amdahl's law. And Amdahl's law is a formula created by a guy named Jean Amdahl, which describes the limiting factor in any parallel algorithm being serial zones in that algorithm. The more serial zones you have in your parallel algorithm, the worse it will scale overall, or the less it will be able to scale. Maybe is a better way to describe that. So it's important when we're thinking about parallel query plans, which are nothing more than really algorithms applied to the query processor, to limit our serial zones. And I talked about a pattern to do that. And I talked about how most algorithms do not scale. For example, sort is extra linear, n times log of n. Sorting 1,000 elements versus sorting 10,000 elements, sorting that 10,000 is more than 10 times slower than sorting the 1,000. So the more that we can decrease the size of our chunks of data within a query plan, even if we have to process a lot of data, the more that we can process smaller chunks in smaller sets, and if we can spread that across lots of CPUs, that's when we get a great benefit. So, of course, there were some demos in that talk, and I'd like to show you the final demo that I showed 2 years ago, just to kind of bring you back into the right mindset. So I'll go over here, and I'm going to jump into AdventureWorks. Whoa, that was weird. And this is a query that I've written. It's called active intervals. And the idea is to find out which products are active for a given interval of n, where n is a number of days. So for example, if I sold a product on Monday, it's still active on Tuesday, and it's still active on Wednesday, and it's still active on Thursday. It's active all the way till next Monday. And the idea is to kind of tell us what we've sold recently or what we've done recently over time. So this query finds all of the active intervals. Let me just start it running because it takes a few seconds. For products 1001 to 3618. And it does this by, I don't know, does it really matter? Probably not. It's a big query, let's just put it that way. And you know, it hits the table a bunch of times and does some joins and some exists, and you know, it's good SQL stuff. Anyway, it's going to run for about 10 more seconds, so I'll just keep talking, you know, fill the dead space for you. Or not. Eventually it's going to finish. And actually it should run slowly, because that's what I want to have happen. Maybe not quite this slowly. What are you going to do? All right. Wow. 36 seconds to run this query. That's meaningless to you. That's fine. 36 seconds. We got product IDs. We got ranges. That's all you need to know. Now, I took this same query, and I rewrote it using the apply pattern that I talked about in the 2012 edition of this talk. And basically, instead of joining, or instead of predicating on product ID here inside of this query, instead add this weird formulation on the outside of the query. Select distinct product ID from big product, but it's not actually the product ID. It's the product ID plus the remainder of 0 divided by the product ID. And of course, 0 divided by the product ID is 0, and the remainder of that is always 0. And this is one of those weird optimizer tricks I mentioned before. So the optimizer doesn't know that. So this forces the optimizer to kind of redistinctify the products, even though there's already a distinct key on there, which forces it down a certain path in the query plan, which I'll show you in a second. Include actual query plan. And then I take that piece of information, and rather than predicate in here on that product ID range, I correlate on that product ID. And we're inside of an outer apply in this part of the query. And then I filter on the correct products out here. So when I run this, instead of 36 seconds, the thing runs in about 4 to 5 seconds. Took 5 that time, took 4 when I ran it earlier. Anyway, this is the same demo I showed earlier, so no reason to be excited about this. If we go to the query plan, the reason that I did that is that if you look here, hit F4, look at the actual number of rows that are coming off of this seek. Actual number of rows per thread, only one thread would have anything to do in this plan had I not played this weird optimizer trick. So what I did was I forced a distinct sort, which made the optimizer choose this repartition in here. It's a hash repartition. And so if we look right after that, we can see that we had good distribution, really nice, even thread distribution. And that's what the whole point of the 2012 talk was getting nice, even thread distribution, making everything into small chunks, getting rid of our repartitions, getting rid of our serial zones, optimizing parallel processing. I also showed a couple of other kind of weird things. For example, let's look back at this query plan. Notice it's a nice parallel query plan. That is, of course, the point. And you'd think, if I added an order by, that not much would change. But you'd be wrong, because now I lose parallelism. SQL Server says, oh, you want to do a little more work? Well, let's just do that on a single core. Let's not use multiple cores if you want to do more work. That's kind of weird, isn't it? And I showed this trick in the 2012 version of the talk to manipulate a row goal. And so I put a top in here, top at I, to make a smaller estimate. And at I is a variable, which I'm going to define here as 2.1 billion, the maximum integer value. So logically, that's the same if I'm sure that there's never going to be more than 2.1 billion rows coming out of that iterator, or coming out of that section of the query. And I'm sure of that. So this is logically the same. And then we can use optimize for right here, and we can optimize as though at I is 1. And that's kind of a cool way to fix this query, I guess. At optimizer time, it's going to build a plan for 1 row, but at runtime, it's going to run the plan for 2 billion rows. So I'm going to get the optimization I want with the output I want, and that brings us back, once I put that in place, to a nice parallel query plan. Great. So how can we do better? That's the question. And that's what we're going to talk about for the rest of our time together today. Let's move back to the slides for a moment. The other thing I did in the 2012 edition of this talk, which is kind of a best practice, is I introduced myself. So I should do that. This slide, however, strikes me as very dated looking at this point. So check out my new introduction slide. Much slicker, don't you think? So I am a SQL architect in Boston area. I focus on the financial services industry, primarily hedge funds and mutual funds and things like that. I build data warehouses. I do data warehousing all day long, every day. Lots of performance tuning and fun and stuff like that. I've written some books and written some articles for magazines. I've written for websites, whatever. I've spoken at PASS a bunch of times. This is, I think, time number 8 for me. Always love speaking here. And I have a website, sqlblog.com. If you go there after, let's say, 3 p.m. today, I'll try to get the demos up there by 3 p.m. today. If they're not up there by 3 p.m. today, they're not going up until probably midday tomorrow. Because, you know, Thursday night at PASS, I'm not going to be sitting in my hotel room posting demos. Sorry. But SQLblog.com, definitely by tomorrow. They'll be there, the demos. If you want to follow me on Twitter, that's at the bottom of this slide. And if you want to email me any questions after this, feel free, amechanic@gmail.com. So what are we going to do today? Well, we're going to build on everything I talked about just now, which is pretty much 90 minutes of content that I condensed down to 5. And we're going to tweak it even further. We're going to talk about influencing costing in hopefully a better way than putting a top with a weird variable in every query where you need it. Because I found that to be a little bit, I don't know, maybe esoteric or weird. Well, I guess everything here is esoteric, but it just kind of feels weird to modify your queries in such a way. So we're going to talk about that, and I have some improvements there. We're going to talk about worker balance and what that really means. Is worker balance really about number of rows, or is it about something else? I thought about this a lot over the last 2 years, and I've come to some different conclusions. And finally, I'm going to talk about taking full control, or at least today's version of full control. Maybe 2 years from now, I'll have even more. But that's where we're going to go today. So let's start with costing. And here's the slide from the 2012 version of the talk, which still works pretty well. How do we cost a parallel plan? Or when I say we, how does the query optimizer cost a parallel plan? Well, first of all, it comes up with a serial version of the plan, or at least a cost for the serial version of the plan. And if that cost exceeds whatever your cost threshold for parallelism is, it takes all the CPU costs. So every iterator in a plan has a CPU cost and an I/O cost. It takes all the CPU costs and it divides them by the DOP, the degree of parallelism. Then it has a number. But then it has to add in the cost for all the parallelism iterators that you see in query plans. Those iterators are not free. Those iterators are actually quite expensive from a CPU perspective. So it has to add back in that cost. So it does some division, which reduces the cost. Then it adds in the additional iterators, which increases the cost again. And now it just compares the serial cost to the parallel cost. If the serial cost is cheaper, it uses the serial plan. If the parallel cost is cheaper, it uses the parallel plan. And that's pretty much all there is to it. And that's why that top hack that I showed before works. Because what I've done there is I've taken advantage of the division, and then I've reduced the parallelism iterator cost overhead by having the optimizer pretend that only one row will ever flow through each of those parallelism iterators. Kind of a dirty hack, but it works. However, there are better ways to fix this problem. And let's go do that now. Yes? The question is, if max DOP is 0, what does that mean? And that means 64 or the number of schedulers that you have. Bad default, by the way, but that's not the topic of today. Let's go over here. So I'm going to go into AdventureWorks, and here is a query that I've come up with. This is a kind of a weird query. And I'm going to go ahead and just look at the query plan. Doesn't matter what the query is doing, really. What matters to me here is that this is a big query. It has an estimated cost of 182, which far exceeds the cost threshold for parallelism that I have set, which is the default of 5. And I'm not getting a parallel query plan here. And the question is, why am I not getting a parallel query plan? And the issue is comes down to really costing. The query optimizer came up with a parallel query plan in this case because this query's serial plan exceeds a cost of 5. And then it did the division, and then it added in the parallelism iterators and said, parallelism is cheaper. Parallelism is more expensive. I'll just use the serial plan. But in fact, that is not the case. I know that because I've tested this. You might not know that without testing it yourself. Feel free. So one option is this trace flag, 8649. This is undocumented and blah, blah, blah. But it basically eliminates the cost overhead and forces the query optimizer to produce a parallel plan if it can produce a parallel plan. And I recommend this thing for using in test environments and development environments and so on. And what I showed in the 2012 version of the talk was using this to debug and figure out where the additional cost was coming from. So it's coming from these parallelism iterators that we see here. And then inserting these top iterators with, a value of 2 billion and going from there and kind of messing up the plan a little bit. And I don't know. It seems to me there's drawbacks to each of these things. So 8649, I wouldn't want to use that in a production environment because it's completely undocumented. I can't use it in a view. And then we have a permissions issue, which I'll show you in a second. Top at I works pretty nicely, but it's kind of tricky to implement. You really have to know what you're doing. It looks complex. Like if you wrote it in a query and then someone else takes over your query 3 or 6 months later or 2 years later and they haven't talked to you, you're going to be like, what is this guy thinking? And finally, just like 8649, you can't use it in a view. And that's kind of annoying to me. I've hit several situations since 2012 where I needed to use these things and kind of embed them somewhere that they could be reused. And if you try to use a hint in a view, like query trace on 8649, you can't do it. It just doesn't work. You can't put a query level hint into a view. You also can't have a variable in a view, which means you can't do top at I. There's nowhere to declare at I in your view. So you're kind of out of luck in this case. You have to modify all the downstream queries. Kind of a headache. I didn't like that. Furthermore, let me go up here and grab this query. And I'm going to go to a new window, and I'm going to connect to my SQL Server using a login called low access. And low access, all it has access to do is connect to AdventureWorks and read data. That's it. So I'm going to connect in here, and go to AdventureWorks, and we'll try to get the query plan, and we can't. User low access does not have permissions to run dbcc trace on. Well, this query trace on option that I have here, under the covers, is really doing a dbcc trace on, and that requires significant permissions. Actually requires sysadmin. Do you want to give all your users sysadmin? I don't. Do you want to? So there's another option. You could go and sign all your modules with certificates. Bit of a pain. So yeah, not good. Neither of these things are good. So I worked on this for a bit, and here's what I came up with. I wrote this function. So I thought about this. Let me just back up. And I thought about what's going on here and what do I need to do? Well, the issue is division occurs, right, on the cost. And then the parallelism iterators are re-added, which then increases sometimes that estimated cost beyond whatever the division gave us. So how can I make that division more effective? Well, the key is to make the numerator a lot bigger. The bigger the numerator, the greater the effect of the denominator in division, right? So what if I can make the numerator really, 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 really big? Then I could guarantee that no matter how much overhead is added due to the parallelism iterators, I'm going to come out ahead. And that's what I did. So here's how we're going to do it. I created this function called makeParallel. And what it is a lot of ones. I love the number 1 so much. It's such a cool number. Do you know 1 is the only number that if you add it to itself a number of times, it will become any other number? That's pretty slick, huh? It's like crazy. So mathematically, very powerful number. Well, I made all these 1s, and here's another modulus. The modulus operator, pretty cool stuff in SQL Server, because the optimizer doesn't know anything about it, but it has some cool features. So 1 divided by 2. What is 1 divided by 2? Well, it's 0 with a remainder of 1. But the optimizer, once again, doesn't know that. So I'm going to ask for this. I want top, and then this is the maximum big integer value from all my number 1s, cross-join to all my number 1s, cross-join to all my number 1s, cross-join to all my number 1s. That's a really, really big number. But I only want rows where 1 divided by 2 equals 0. So there's no rows. But the optimizer doesn't know that. It doesn't know how many rows there are, so it's going to give me an estimate of some big number. We'll look at it in a second. And then I want the sum of all those numbers where the sum is null. And this is kind of key. This guarantees that there will always be 1 row returned from this function because the sum is always null. So I created this function, and what we can do is use it in any query. I'm going to go into AdventureWorks. It does not matter what your permissions are. And I say select x.star, where x is a derived table right here, which I am joining to. You can use either cross-join or cross-apply. I kind of like the way cross-apply looks better. It just, I don't know, I just like the word apply. Anyway, select x.star from dbo.makeParallel, cross-apply to the query, or cross-join to the query. Again, it doesn't matter. And what makeParallel is going to do is come up with this huge estimate. Let's look at the query plan. So here it is. Let me just expand it a bit. And so we have this big, huge estimate over here, right? It's going to estimate, let's take a look, that many rows. I don't know what that number is. That's a big number of rows that it's estimating. And as a result of that estimate, the subtree cost is absolutely ginormous. And once you divide that, there's no way the parallelism iterators are ever going to take over. So we're good to go no matter what with this function. And then under here, under this nested loop, is our real query, which basically uses the same parallel plan we saw before, but now it's just showing up under that nested loop. And when I run this, oh, you know, I forgot to put on an actual query plan. I apologize. So I'm going to run this query, and it'll take hopefully not more than a few seconds to run. There it is. And when I run it, what happens at runtime is that 1,000 rows, or 1,024 rows, come out of this constant scan. They're immediately filtered by that predicate. Remember that 1 divided by 2 is never 0. So they're immediately filtered by that predicate, and then nothing else happens here. So the entire cost of making this plan parallel was scanning 1,000 rows and getting rid of them. All the rest is just estimate. And that's all that matters when coming up with parallel plans, is influencing the estimate. So I've added almost nothing, and I can guarantee a parallel plan. Furthermore, because this is nothing more than a user-defined function, and because it doesn't use any variables or anything like that, I can put this in a view. I can use it in an inline UDF. I can use it for any user, anytime, doesn't matter. So give that a try. It's just as undocumented and just as unguaranteed as 8649, I should add, or top, or anything else, but I think it's a little cleaner. Yes, sir? What about memory grants? Good question. There's no memory grant here. And the reason that there's no memory grant here is there are no memory-consuming iterators except for this one, the parallelism. So the memory-consuming iterators that we need to be concerned with are sort and hash. Exchange iterators also consume memory, but they only consume a few pages at a time. So we really don't need to worry about it in this case. Yes, sir? Is there a similar technique to fake it out, to grant more memory to hashes, to avoid spills? Absolutely. And not on topic for this talk, unfortunately, but if you search, there was a SQL Rally conference last year in Sweden and Amsterdam, and I gave a talk at each of them, and I believe both of them are online. I give the same talk, and that talk shows how to do that. So search for that. And it actually uses actually, I wrote the function the same week I wrote this one. It also uses a function. So, with lots of ones in it. So I like ones. Any other questions at this point? Is there one back there? Or? I can't see that far, I apologize. No, that's someone wearing like a weird rainbow hoodie. Hello. Okay, so let's move on. And what we just saw, or what we saw in the first part of that demo, or maybe it was the prior demo, was the parallel apply pattern that I introduced last. That's what we saw in that first demo I showed, was the parallel apply pattern that I introduced last time. And the parallel apply pattern, again, is where we take our driver set, in this case it was a distinct set of products, and we drive our query. So instead of doing, for example, if I need to sort order by product ID and something else, instead of sorting the entire set of data, all the products in one monolithic chunk, I do one sort per product. And that's where we can take advantage of the mathematical fact that algorithms don't tend to scale very well. So we drive, in terms of chunks, into a correlated payload. So for each product, we're correlating on product ID. We do our sort or our hash, or our joins, or whatever it is we need to do. And that's the parallel apply pattern. And one of the things I talked about pretty extensively last time was how much I disliked parallel scan. So parallel scan works. It can be a table scan. It can be a range scan, which is a seek with a scan. Or it can be a clustered index scan. Any of these in a parallel zone can be a parallel scan. And what parallel scan does internally is it doesn't read data on a row-by-row basis, but rather it feeds data out on a page-by-page basis, or even in chunks of 32 pages, depending on statistics. So you can get into situations where you have a really dense page, let's say on product IDs. That's why we only had one thread doing any work in that demo I showed before, because we had enough density on our page that a single page had all of the product IDs we asked for. And so we can get a lot of skew from this. The nice thing about parallel scan, however, is that it uses a demand-based scheme, whereas the repartitioning tricks that I showed, for example, the distinct, and then you'll see a top in just a bit, the repartitioning tricks, they don't use a demand-based scheme. They use kind of a preordained distribution scheme where rows are either distributed using a round-robin algorithm, next row to next thread, next row to next thread, or they're distributed using a hash algorithm. Either way, it's not demand-based, it's fixed. So if one thread has more work to do than another thread, you might get yourself into some problems. And on that note, I'm going to show a little, what I call, magic trick. Okay, so let me close this out. Close this out. So here's yet another version of that active intervals query that I showed before. And I'm going to just start it running, because again, it takes a few seconds. Let me just select it and run it, because there's something below it. And I have it not very hooked up, just to recompile. Okay, there we go. Now, this is almost the same as the one before, but I've swapped out the reference to the big transaction history table with another table called big transaction history underscore UE. Get to what that means in a bit. And I've changed the product range a little bit, and that's it. Now we feed this, our driver set there. The query just finished, took 20 seconds to run, and our driver set is this guy. So there's the results, in case you care. Our driver set is this guy. Select top, and then maximum integer value product ID from dbo.bigProduct, where the product ID between min and max. Pretty simple driver set. And what that does, I really should have turned on actual query plan again. Let's run that again. So what that does, and we'll see this in 1 second, is it forces, this top forces a serial zone into the plan. And then the optimizer needs to get those rows back into a parallel zone to continue processing the remainder of the plan in parallel. So it introduces a round-robin redistribution in the plan, giving us completely even thread distribution. So there, it took 21 seconds. It's actually slower the second time I ran it, probably because of the execution plan. And what we can see is our top caused a serial zone to come into the plan, and then that feeds into this distribute streams, which uses the round-robin algorithm. And the results of that algorithm is very nice, very even distribution of rows across our threads, right? Perfectly even, exactly what I was talking about in 2012. Very nice stuff. Well, now the magic trick. So select top product ID from big product. I'm going to swap that out for this. I have this table called big product UEC, and it's just a bunch of product IDs, right? Same product IDs. I'm going to put it in here. No top, no distinct, nothing like that. I'm going to run the query again. And now, something very interesting should happen if my demo works. It'll run for a few seconds, just like before, but hopefully, here's where I get nervous. Oh, it took 16, it was supposed to take 15. Anyway, it takes 15, 16 instead of 20, 21. Okay, anyway, it ran faster than the other one. That's the important point. It ran faster, And gone is my serial zone. Gone is my redistribute. In its place is an index scan. And let's check out the thread balance. The thread balance has gone crazy. I've introduced imbalance in my query plan. The exact thing I said you should do. Force balance. I've removed the balance, and the plan is faster. What gives? Sorry? The cost, no, actually the cost for the redistribute stream is very cheap in this case. That's a very small number of rows. Was not the serial part that caused that. Some rows are big. Oh, hold on, hold that thought for 1 second. Oh, we have some very smart people now. Or else I'm being way too obvious. I'll say he's smart. So, let's go back to the slides. And let's consider these 28 units of work. Exactly. We have 27 small units. So each of these boxes is like a unit of work. We have 27 small units and one really big unit of work. Okay, that's the green guy. They're all just rows that need to be processed. And so we'll say maybe each of these boxes has to do with a product or something. Now, if we use a hash or round robin scheme to distribute these across our threads, what's going to happen? Well, it's going to very equally distribute the units of work across the threads, and it's preordained. So even as threads 1, 2, and 4 finish, thread 3 is going to keep working, and those other units of work that kind of come after the green big blob, those are still going to go on thread 3, even though threads 1, 2, and 4 are sitting there idle. And that's what we're forcing when we force a repartition, unfortunately. So if our data is very, very equal, then that's not a problem. But if our data has various spikes and jags, now we can be getting ourselves into a bit of hot water. As it turns out, a lot of real data sets have spikes and jags and big pieces and small pieces. I mean, you might sell 1 million units of Coca-Cola and only 10 units of Pepsi or something like that. Coca-Cola is a SQL Server customer. I don't know about Pepsi, so hopefully I didn't insult anyone. But anyway, imagine if we were able to switch over and make good use of a demand-based scheme. A demand-based scheme that didn't have skew, however. That would be nice. Thread 1 would ask for some work, and then thread 2 would ask for some work, and thread 3, and thread 4. And then when each of the threads were done with the work that they had, they would ask for a little more, and a little more, and a little more. Finally, maybe thread 1 will get the big unit of work, but threads 2, 3, and 4, they would keep on working, and keep on working, and keep on working. And we get a much more balanced version of the plan. So how can we make SQL Server do that for us without introducing skew? Right? That's the whole problem, is that demand scheme introduces skew due to different page densities and so on. We want to get rid of that, but we still want to take advantage of the good stuff. Well, let's go ahead and see. So let me just close this down. And what I did to make this work, I started thinking about how the demand scheme works, and it works on a page-by-page basis, or, again, big, huge chunks of pages. And I thought, what if I actually just work with page by page? And what if I create a table with 1 row per page? What would happen then? Well, each page will be a row. Each time a request is made into the demand scheme, rather than getting a whole page full of rows, I just get 1 row at a time. Pretty cool? Well, yeah. Not bad. So I created a table called loop ranges. Originally, when I started playing with this a couple years ago, I actually created 1 number per page. And so each page is 8,060 bytes, and I created 1 million numbers just to seed it. And I think I blew up my log file after a couple minutes. So what I decided to do instead was kind of split the difference. And I put in a start and end range on each page, and then I put a filler column to kind of fill up the rest of the space and force 1 page per row. And so here's what I ended up doing. I do 100 numbers per page, effectively. It's actually a range of 1 to 100 per page. And then I replicate the letter X 8,000 times in order to fill up each of the pages. I also have a little function we're going to use here to test this. So let's just select from the table so I can show you what it looks like. So this is what the table looks like. And so 0 to 99, 100 to 199, and so on. There's 100,000 rows here. So if I had product IDs ranging somewhere from 0 to 10 million, I'm covered. And each request into here will give the thread 100 products to work on. And over time, we'll get all the products taken care of, hopefully, in our query. So let's go back here. And I want to test this thing and see what happens. So what I'm asking for is rows from the loop ranges table where the start is between 0 and 1199. So I just want to read about 12 rows worth of data. And for each row, I'm going to go in and read from this sleep function. Sleep function is just a CLR function I built. The deploy for that is right up here. And all it does is it sleeps for however many milliseconds we ask for, just to kind of simulate some work. And I'm doing this just to make a kind of simple query plan that we can test. And so it'll sleep for 250 milliseconds per row. And I hinted it up just to kind of force the plan shape I'm after. Query, include actual execution plan. I'm going to run this thing. OK, so that took about 3 seconds to run. Here's the query plan. We got a parallel scan off of our loop ranges table. For each row, went into this nested loop, and then went into this constant scan, which calls into that sleep function, sleeps. Now, it took 3 seconds, and let's check this out and see what our thread distribution was. Well, even though I had 1 row per page, I still got uneven thread distribution. Turns out, in some cases, you get 1 page per request into parallel scan, and in some cases, you get 32. So how do you control that? We need to start messing with statistics, unfortunately. So turns out there's 2 things that go into this. First of them is number of pages. If the estimated page count for the table is less than or equal to 500, we get 1 page per request. If it's greater than or equal to 500, we get 32. So I'm going to make it 499. There we go. Now I'm going to run this again. Instead of 3 seconds, it runs almost instantly. And the reason it ran that fast is that now something has changed. And now we have a nice, equal thread distribution. But it's using demand scheme, which is also nice. Unfortunately, in addition to the page count, we also have to control the row count. If I up the row count too high, and the deal here is if I up it to an estimate of over 1 million, we're back to 3 seconds. And once again, we are back to a completely uneven and skewed row count. So what we need is perfection, and nothing less. And that's this. So we want a row count estimate of just under 1 million and a page count estimate of just under 500, which guarantees 1 page per request into that parallel scan. So I'm going to put that back like that. And then let me show you how you could actually use this in a real query if you wanted to. And I've used it a lot of times in real queries. It works pretty well. So here's the same query yet again. This time we're going to start with our loop ranges table. So that's going to be kind of our main outer. So there's going to be an outer driver and then an inner driver. And the reason we're going to have both is that we want to filter and only touch the actual numbers which correspond to real product IDs in our system. We don't want to go off and ask for ranges of data that either don't exist or that we don't actually want to touch in our query. We just kind of want to use this to control the query. So we're going to ask for a range start and range end from loop ranges, where the range start and range end intersect with our minimum and maximum product IDs. Then, in the apply, I'm going to go out to the actual product table, and I had to put a force secant in here to make the query optimizer play ball with me. And we want product IDs. So this is, again, going to be on a row-by-row basis. We want all the product IDs that are in range. But our range might be bigger or smaller than the actual ranges on each page. So I have to use this case expression for both the start and the end. to truncate things down and get only the actual product IDs that I'm interested in processing in any given point. And the result, I'm not going to actually run it because it'll just give some more results, but we'll look at the query plan. Actually, I can run it, why not? All right, so I'm going to run that, and what we'll see is the demand scheme kicking in eventually. Okay, there we go. And what we'll see is, if we look out here, we have read 91 pages from our table, and you can see the balance is a little bit off. It's even further highlighted if we jump in here to the product table. So we read rows from here, and then we read rows from there, and then that table was used to actually control all of the real stuff. So I've taken the apply pattern, and I've just kind of wrapped it in a further outer apply pattern. And so when I click here, we see that the actual number of rows requested per thread is rather unbalanced, and yet performance was pretty decent, again, as compared to that first query that I ran. And this is, again, because we're using a pure demand-based scheme now, and we're forcing the optimizer down that path, which is pretty nice. So I'm quite happy with this, but, of course, it has some downsides. Downside number one is this one, SP space used. Every single time my query runs, I'm scanning up to 800 megs of basically useless information that's just there for control. Probably not ideal. Likewise, I have to store 800, well, that's 800 megs if my product ID range is constrained. If it gets bigger, I have to store more data, and I have to maintain that data. And if my stats job comes and re-updates my stats, this can break on me. Now, there's obviously things we can do to control all this, but it's less than ideal. Would you agree? Any questions, by the way, before we move on? All right. So what we've just seen is the demand scheme and kind of some of the benefits and one way that we can make that happen. But even better than a straight demand scheme would be a demand scheme that we control a little further and do size weighting. Now, on our demand scheme before, if we just do a basic demand scheme, that big green block of work can come at any time, whenever we get lucky enough to request it. Maybe all of the threads have already done almost all the work, and then the big green block comes, and now one of the threads still has to do a lot more work. What if we could size weight the demand scheme so that the big green block comes out first, and then all the little blue blocks kind of fill in the gaps? It's like a game of Tetris in SQL Server. Kind of fun. What if we could do that? Then we could make sure we always have absolutely optimal performance in every single case, which is, of course, well, it's my goal. I don't know about you. So we have a little problem. SQL Server doesn't have a feature that does this. I want it. Okay, that's my problem at least. SQL Server gives us either a page-based demand scheme that doesn't really work 100% of the time for me unless I kind of hack it and do weird stuff, and then even then I can't control it and get it size weighted. It gives me a key-based, nice and balanced scheme, which I've already showed doesn't really work. What I want, what I need, is key-based demand scheme, which is again size weighted. So how am I going to solve this problem? Well, I can either stop caring about the problem. I'm sure some of you are like, what did I get myself into? This is ridiculous. Who is this guy? God, I have a headache. Is it lunchtime yet? Well, that's one option, or just leave. But for me, I love this stuff, so I am going to go with option C. We're going to roll our own. Yes. And what does that mean? That means the evilness of SQL CLR. All right. So let's take control. Get back out to the demo. And, oh, I forgot to show you something. Apologies. So I wanted to show you actually what big transaction history UE means. Anyone guess what UE stands for? Stands for uneven. So the original big transaction history table had about 1,000 rows, or maybe it was 2,000, something like 2,000 rows per product or something like that. This one has kind of a variable number of rows. Actually, let's go down here where I define the rows. It has exactly 1,000. They're kind of weighted actually a little bit, so it's not exactly 1,000 per product. But then I made some of the products have 1,000 times more rows. And I did that on purpose to make those plans especially difficult. And then I flipped over from there to this table called Big Product UEC, which stands for Big Product Uneven with Count. And so that's nothing more than one page per product ID, because I've replicated X 8,000 times, and then a count. And then I really cheated. I did two things. First of all, I created a unique clustered index on product ID. And distinctness really matters with query optimization. We'll see this a little bit more in just a bit. So I needed a distinct predicate, but what I wanted to have happen, I wanted the query processor to scan a count-weighted index. That's not a count-weighted index. That's just an index sorted on product ID. Now the count-weighted index is this one. It's actually C, that's my count descending, and then product ID. And then I really cheated. I put a filter on this index for the exact product range that I showed. And it turns out that the big product in this chunk is like 28,900 something. So that's why it was magic trick. I completely cheated and prepared it. But what if I didn't want to prepare that in real time? That's the question. Because obviously you can't do this every time you run some report or something. That's not going to happen. So here's what I've come up with. I've written this set of CLR functions that can handle this situation for us. And this is just a deploy that you can get in the download. You just connect to your database if you trust me enough. Hit F5. Put it right in prod. Don't worry about it. I promise it probably won't crash. Well, it hasn't yet. Anyway, I wrote it on the plane on the way here, so it should be fine. So here's how it works. There's two flavors. There's a range-based one and a weighted one. So we'll start with the range-based one. It's a little bit simpler. And so the main outer function is called parallel driver ranged initializer. You give it a SPID that you're working on. So that so basically, all of the threads are going to run. And of course, they're all in the same SPID. But within the CLR space, I can't tell which SPID you're on based on any information I can pull in there. All I get is a managed thread ID. So you kind of have to pass in your SPID so that all the threads can talk to each other and coordinate. So don't pass a weird fake SPID in here is the moral of the story. So you pass in a SPID, and you pass in the range you want to initialize. And what this does is it returns 256 rows of just arbitrary, monotomically increasing values that have nothing to do with the range you're after. The reason that it does that is that it's designed to actually go into a hash or round-robin repartition and saturate it and make sure that at least one row gets to each thread. Now, if there's more than one row on some of the threads, that's fine. It'll just throw them out. But each thread inside of the nested loop needs at least one row so it can kick off the inner part. And the inner part is this. So this will show up on the inside of an apply. So we initialize, which sends out 256 rows. But then on the inside, this function, parallel driver get numbers, takes again the SPID, and then it takes a reference to parallel driver ranged init.I, which again is just this arbitrary number that's there to force the query optimizer down a certain path. And what we'll see when I run this is we'll get all the numbers from 1 to 5,000. Here they are. But only that first row of I is actually used. The rest of them are just thrown out. And if I had multiple threads, each thread would use the first row it gets for I, and it would ask for numbers, and it's all demand-based. So it all asks for the next number, next number, next number, only when it's done working with the prior number. So it's key-driven, demand-based. So let's try using it in a query. And here is the same query as before. Select I from parallel driver ranged init. Outer apply, select number as product ID from parallel driver get numbers, Each thread now, let's look at the query plan. Each thread is going to, well, hold on. There we go. So out here on the outer side of my nested loop, we initialize, then go into a hash distribution. I send in enough rows to guarantee that each thread will get at least one of them. And then inside of this nested loop, down here, each thread starts asking for numbers. Now, unfortunately, we have two big, huge problems in this plan. And they are table spool 1 and table spool 2. Now, table spools are hidden tables in TempDB, populated in real time by the query processor. And the last thing I want the query processor doing while it's running my plan is creating temp tables. I'm doing everything to improve performance, and it wants to go right to the disk. Not cool. Now, why is it doing this? Well, it's doing both of them because of lack of distinctness information. It's creating this one because it thinks that the correlation value, I, might not be distinct. So what we'll do is we'll replay the same data every time we get a repeated I. Well, that's not necessary, but we have to tell it that. It does this one because it doesn't know if the numbers from our parallel driver get numbers function are unique. So, hey, same thing. I'm going to help you out. Well, no, you're not, but thanks for trying. So let's fix the problem. Now, I could put a distinct, or I did put a distinct here. Select distinct I, and I is, in fact, distinct. So that's good. I also put a distinct down here, select distinct number from parallel driver get numbers. Now, let's look at this plan and see what happens. All right, so our outer table spool is gone. Excellent. Got rid of it because we've told the optimizer that we're distinct. Our inner table spool under get numbers is also gone. Great. Not so great. Because we asked for distinct, SQL Server introduced a hash match iterator, which is a blocking iterator, which means each thread is going to come in, start asking for numbers, get all the numbers before any work is done, balance them out really nicely, which is the exact opposite of what we want to have happen, because we want it to be demand-based and work-based, and then start doing the work. So that's not good. So the solution is a little bit weird. Yes, it's going to get even weirder. And it's this. So if we go back here, we can see the estimate is 1,000. All CLR functions, table value functions, have an estimate of 1,000. Well, we need distinctness because SQL Server knows or estimates that there's going to be more than one row and thinks that some of them may be non-distinct. If we want to eliminate the need for distinctness, we need SQL Server to estimate that there will only be one row. So here's a ridiculous formula I came up with to make that happen. What I do is cross-apply to select some number from the number for each number, and then do the same again. And then I join where the number equals the sum of the number, but the optimizer doesn't know that, so it reduces by a factor of 10. And the number equals the same sum of the number, but it's in a different query, so the optimizer doesn't know it's the same, so it reduces it again by a factor of 10. And the number equals the checksum of the number, which is the same number, and the optimizer reduces it again by a factor of 10. I told you it was a little bit ridiculous. If anyone comes up with a simpler way to do this, by the way, let me know. Seriously. And let me turn on the actual query plan. And what we'll see, I told you at the beginning this was going to be a little bit ridiculous, so I am a man of my word. Please. The question is, could you use the top 100% instead of using top at integer? Well, you could, but you wouldn't get what you were after, because top 100% will just be optimized out. So the top at integer works because of the optimize for at the bottom, and I optimize as though the integer is something. In that case, it was 1. But top 100% is always 100%. It's always everything. So it can't be optimized that way. Now, if we look at the query plan, here's what happened. This thing returned 256 rows, and they were distributed. So we had, forgot to hit F4. So we had nice, even thread distribution. Excellent. Not completely even, but even enough, it doesn't matter how even it is. Because again, we only need one row per thread. In here, parallel driver get numbers started running. Notice that there's no distinct operator here, no blocking operator. There's no spool because my estimate coming off of this, actually I think the estimate is over here. Estimate 10, I thought I got it down to 1, but I guess maybe it's this, whatever. Close enough. So the estimate was close enough to 1 that it, oh wait, it's this filter. There's too many filters here. There's the estimated number of rows is 1, and that's what made it not put in the table spool, because there's no reason to spool one row, right? Meanwhile, though, what actually came off of here were 9,000 rows, and you can see our demand scheme playing very nicely and balancing everything very nicely, and that's exactly what we like. So that's how this one works, and then we just have, oh, that went quickly. We just have a few minutes left, so I'm going to just show you the weighted version. So again, over to AdventureWorks, and the way that we maintain the weight, or at least one way to do it, is to create an index view. And I know many of you have probably been burned by index views in the past. So this is not the only way to do this. You could create an index view, or you could do a background process of some sort. That's something else I've done. That kind of occasionally, this doesn't have to be 100% exact. It just kind of has to be more or less exact. Or more or less kind of in the ballpark. So you can use an index view. You can create a background process. You could even, if you're really, really insane, you could try to do something with SQL Server's own statistics and kind of try to figure out some numbers and some weightings. I actually think index views that are small, like this one, really small, really targeted, have very little overhead and don't really cause a lot of problems, but this is something you'd really want to test in your environment. I've used this even in fairly large data warehouses, and it's worked pretty well. So this index view is very simple. It's just product ID, count big star from big transaction history UE, create a clustered index on product ID. And now I have another function I've introduced, and this is called parallel driver weighted aggregate. And it takes the product ID and the count, and what it does is it ingests all of the product IDs and the counts from the indexed view. I'm putting the entire set in this time, but you can do just a subset, and then it sorts them by the count. That's all it does, and then it holds it in memory, gets it ready to output. So I'm going to do that, and the number it outputs is just a random number. It's basically a pointer to the memory location where the data now sits. So you don't have to worry about that. So now I take that function, parallel driver weighted aggregate, I feed it into an initialization function called parallel driver weighted initializer, and then I can call the same get numbers function against that. And basically works the same way as before, except this time it outputs the numbers ordered by count descending and then number descending, if we need to break ties. And that's why we get kind of 50,000 up here, and then these weird numbers, and then we get all the equivalent ones coming after that. So we get all the heaviest hitters up front, and then the lower ones. And we use it in the query the same exact way as before. Aggregate for the products we're interested in. Initialize. Select distinct initializer.i. Apply. Go out to our numbers. Reduce the estimate to 1 so that we don't get some bizarre table spool. And then apply into the actual query to get the data we actually care about. And the results of this oh, man, I forgot the actual query plan. As it runs and runs and runs. Oh, the CPU cost is, I was going to show you how nice, you can see how nicely balanced the CPUs were for the last millisecond that it ran. So you can trust me on that. But is the CPU cost itself for the CLR stuff pretty low? Yeah, very low. All it's doing is taking a small set of numbers, sorting them, and then just spitting them out one at a time from an array. So it's very simple. Actually, this is very simple to write and to kind of imagine. It's interesting that SQL Server is able to do this without my playing around. But anyway, the result of this is, so we calculated the weights, ran in order, and in this case, completely unbalanced, and that's what we wanted, perfection. So we're just about out of time, but I think I could take maybe one or two questions, if there are any. Yes. The question is, why did I use MaxStop? And the reason is because my laptop is annoying, and I was getting an issue with my CPUs. I have 8 cores, but they were getting all bound up together, so I just put MaxStop in to limit it a little bit. Would I still use MaxStop in a real query? No, I would actually try to control it at the server level, or resource governor, if possible. In the back? Does this work with column store? Well, in theory, it works with column store, but interestingly, for these queries, I had another demo, but I knew I wouldn't have time. I put it against a column store index, and it becomes 10 times slower. So best of luck to you. Anyway, if you have any more questions, I'm going to be here. I'll just stand here, and we can chat. Thank you so much for joining me today. Thank you.